The other example that we would have done in class today is related to calculating collision frequency and mean free path for a very different sort of system than we talked about during the lectures, and that's for astronomy. So thinking about something out in space in between the stars, the area called the interstellar medium. And in this region, we can have dense, I'll put that in quotes because dense to an astronomer means something very different than dense to a chemist on Earth. But dense molecular clouds out in space have a density equal to about 10 to the 6th particles per cubic centimeter. And mostly this is H2 molecules in a dense cloud. You have trace amounts of other things, including hydrogen atoms is the second most abundant thing, and then you have other molecules things like carbon monoxide, and H3 plus is another molecule. Anyway, but most of it's H2, and we're going to use that as our example. So the other things we need to know to calculate a collision frequency and a mean free path are what's the temperature, and the temperature in dense molecular clouds is about 20 Kelvin. And the other thing we need is the cross-section. So the collision cross-section for H2, we can look it up in your textbook, and we get a value of 0.230 square nanometers. And so we can then, if we have this information, we can find ZA, right, the collision cross-section, and the mean free path L. And what are those in this environment? So I'd encourage you actually to pause the video here and try and work through this on your own. You should have all the information here that you need and the equations that are in your textbook or in the previous lecture videos. So go ahead, pause this, try and work this out on your own, and then I would encourage you to come back and double check your work with me. So I'm going to go ahead and solve this now, but I'd like you to try and solve it on your own first, and then come back, check your work, make sure you get the same answer that I get, and you can check and see how I did everything too. So in class, we would have done this in groups, and you all would have been able to work together. But unfortunately, we can't do that this time. Okay, so the things we need, we have like two of the things we already need. We already have the density here, and we have the collision cross-section. So mostly what we need to do is, these are in different units, right? We have cubic centimeters here, we have square nanometers here. We'd like to convert these to just everything to meters, just to keep things simple, keep everything in meters, because we're going to have the speed in meters per second as well. So our first step is just to convert this density, which goes directly into the collision frequency calculation, to a per cubic meter instead of per cubic centimeter. So we have 10 to the 6 per cubic centimeter. I'll just leave off the particles for now. And so we need to convert that to meters, so we have 100 centimeters per meter. But since this is cubed, we have to cube this conversion factor as well. So 100 cubed is 10 to the 6th, so 10 to the 2nd raised to the 3rd, so that gives us 10 to the 6th. Multiplied by 10 to the 6th gives us 10 to the 12th. You can also just put that into your calculator. 10 to the 12th, and that'll be in units of meters to the minus 3. Particles per cubic meter. So again, I just left off the particles. The other conversion factor we need to do is sigma, because we were given that in square nanometers, and we need to convert that to square meters. All right, so we know there are 10 to the 9th nanometers for every 1 meter, and again we're going to have to square that, and that'll give us 0.230 times 10 to the minus 18th square meters. We could write this as 2.3 times 10 to the minus 17th as well, or 10 to the minus 19th. But it's convenient. 10 to the minus 9 is nanometers, and so therefore 10 to the minus 9 squared is 10 to the minus 18. However you want to do it. Okay, so then the last thing we need is the average speed of the molecule. And so that is going to be given by the formula that comes from kinetic molecular theory. We have 8RT over pi m. And this is a capital M. This is the molecular weight. And since this is hydrogen, H2, that we're talking about, M is equal to, we're going to express this in kilograms per mole, 0.002 kilograms per mole. So then we can plug everything in. So 8 times our value of R, we're going to use the version with joules per mole Kelvin so that all of our units will cancel. We're at 20 Kelvin was the temperature we were given. Pi is pi, and 0.002 kilograms per mole. And the kilograms will cancel in the joules, which will leave us meters squared over seconds squared, which will give us meters per second. So all of our units work out because the moles and Kelvin are going to cancel as well. So if we plug all those numbers into your calculator, you should get a average speed of 460 meters per second. And now we have everything we need to calculate the collision frequency, ZA. ZA is given again by density times the collision cross-section times the square root of 2 times the average speed. All right, and so if we put all those numbers in that we have from above, so again, our density is 10 to the 12th per cubic meter. Our sigma is 0.230 times 10 to the minus 18th square meters times the square root of 2 times 460 meters per second. So we can see all of our meters are going to cancel, and we'll have just per second, which gives us a frequency, which is what we want. And if we do all that, we get a very small number, 0.00015 collisions per second. Now that is much, much less than we got for atmosphere. So the Earth's atmosphere, instead we were getting billions of collisions per second. Here we're getting 1.5 times 10 to the minus 4 collisions per second. An alternative way to think of this is how many seconds does it take between collisions that happen out in space. So if we take the inverse of this, right, if we do 1 over this number, that'll give us the amount of time between collisions instead of collisions per second. So 1 over ZA is equal to 6,700 seconds per collision. So it takes about 1.9 hours between collisions. So if you're out in space in this dense, again, quotes around that dense cloud, it takes about 2 hours for one molecule to find the other one and hit it, which is crazy. The other thing we can do is, since we've calculated the average speed and the collision rate, it's pretty straightforward to calculate the mean free path. We can use this version of the equation, right? Sort of like the definition is if you take the speed divided by the rate at which collisions happen, that'll tell you the time it takes, right? Basically, how far does the particle travel in 1.9 hours, right? Between on average between collisions. So we can take our 460 meters per second divided by 0.00015 collisions per second. And so we'll get how many meters per collision, which is the mean free path, which gives us 3.1 times 10 to the 6 meters for the mean free path. Or if we want to write that in kilometers, that's about 310 kilometers. So the particle takes about 2 hours and it travels 310 kilometers before it finds another particle and hits it. So that's part of the reason space is so different than it is here on Earth. Whereas here on Earth, the mean free path for nitrogen molecules in the atmosphere was only about a few nanometers. Here we're now talking about kilometers, and so reactions occur on a much longer time scale in space, just because the molecules don't see each other very often. So hopefully that was interesting to see, and hopefully that matched up with your own calculations and was interesting for you to see how these look in a very different environment than on Earth.